Arne Nysveen is going to explain to us the generator and the power system within a limited time scale, so this will be quite interesting. And he brought props to the benefit of people like me who understand nothing about this topic. So thank you very much for agreeing to do this, Arne.
Yes, thank you. Maybe it was a weak moment and saying yes to this challenge, so we'll do our best then. So let's say we'll try to explain shortly how a generator is working and a little bit about the power system. So here, let's say to see the importance of electricity on the power system. This is the lower part of Manhattan. It lives almost 5 million here, and the only way to sustain this type of civilization, you need electric power. Okay, so how did it all start? It started by a Danish physicist, Hans Christian Ørsted. He had an amazing discovery, quite simple. In fact, he had a compass needle, or at least some magnetic steel, and then he put current through a loop, and he saw that the magnetic needle was tilting when you put on or off the current. And this was maybe not shocking, but almost, since before this they thought that the electric world and the magnetic world was totally different. They knew about both phenomena. You have the lightning and so on, and you have a magnetic stone, but not that these two were together or has any interconnection. He reported this finding and sent a letter to his friend in France, Ampere, and his first explanation was that, the electric current make the conductor magnetic. That was not a bad thought then. But later on they figured out that it was a force field, the magnetic field. We should be very glad that Ørsted was one of the really pioneers. The result is that all the terms and all the theory for magnetics or electromagnetics is in our own language, in Danish, that is in written Norwegian as well. So this was that the discovery, an electric current could set up a magnetic field. What about vice versa, that a magnetic field could set up an electric current? That was solved 11 years later by Michael Faraday. It was a very intense period how to figure out this one. And what they saw then was that it is not so easy to have the opposite connection at DC. You need to alter something. What he discovered is that if you had let's say a coil or a loop of conductors, and if he was able to change the magnetic field through this coil, then there was a voltage or an electric field. And he was doing a lot of experiments, and they figured out that it doesn't matter how you are doing the change, if you are moving the two magnets together or if you are alternating the current or whatever. How you provide the change do not have any influence on the size. But it's always opposing. So what is happening is that if you have a current going through or a magnetic flux through this coil, if you try to increase it, there will be induced currents in the coil trying to reduce it. But the nature is always losing, and that is why we can use this one. So 2 discoveries, the magnetic induction, and that you could create a magnetic field by current. So that is what we are doing in an electric machine. Here is a cross-sectional area of a machine. So this is the rotor. This one rotates around like this, and this is the stator. So here I have a model trying to show you this rotor part. So this is the red windings, that's the copper here. It's just a coil going like this. Okay? And when you we only have copper on one of these, let's say, poles here. But if you put on a current here, there will be a magnetic field from this one, let's say, going up. And then you need a return path, and that is in the stator then. So this is how we set up the field. So then we're using the first discovery by Ørsted, putting current through a DC current, through a coil, setting up a magnetic field. And then if you, let's say, place another coil, if I now put this around this rotor, then you see when it is up here, all the flux go through this coil then. So there is a very large flux going through the coil. When it has rotated like this, it is much smaller, and here it will be altered the other way then. So it's illustrated here. Here I have my coil. It's a cross-section of the coil. That is this one. So if I now turn this around then I should be able to induce a voltage, something like this. Maybe not that sinusoidal, but almost. So when turning this around this one, I will be able to induce a voltage in this winding. So that is using the other discovery, the Faraday's induction. So here we're using, first setting up a magnetic field by having current here, then place winding in a stationary part. Then when this rotates, then we have a flux variation in these windings, and we induce voltages. So far, so good. The next is, this is really the trick. We are putting 3 phases. We are not putting in exactly like this one, but in this model, it is shown we are having 3 phases. So the first one, A, goes in here, into the screen, and then back, let's say, and come back out again here. Okay, that is one. And then the next one is 120 degrees displaced to this one here. And then the last one is again 120 degrees. So they are displaced like this. So if I now turn this one, I will generate these 3 voltages, and I can measure it. I can demonstrate it here later, that I can generate that in this machine. So that is the clue then. Observe one thing that is important here. If you see that when this phase is at 100% maximum positive, the 2 others is minus 50%. That always happens. And also if you add them together, the sum is always 0. So, okay, if I now do it like this, I'm creating the magnet here, I'm winding the same thing like there. So if I now turn this around, it should be induced a voltage then. Okay, if I do that, I will do it later, then you will have a current flowing that is having the same shape then. And then comes the really interesting thing. If you go back to these displaced windings, if you now take phase A, this comes out here, it goes in here, and comes out at the top. Then when the current here is at maximum, then you can say that this coil, that could be the coil, let's say, it's not so easy to see here. But then this coil, when the current is 1, sets up a magnetic field that goes like this. And we illustrate that with an arrow in this direction. This coil B that is here, that sets up a magnetic field that could go either up or down depending on the direction of the current. But when A is at maximum positive, B is at 1/2 minus, so it sets up a flux here. The same with C, it sets up a flux here. If you add these together, you get this shape, but the amplitude is 3 divided by 2 of what one phase is setting up. Okay, so then we are here. A little bit later, then phase C is having the maximum current. Then C is here, 2 other minus half. still we have an arrow like this, amplitude constant. And then if you go later on to phase B, you see then that the resulting magnetic field has moved like this. And if you do this for all time steps, you will see that if you are putting on a load like this, 3 bulbs here, you will have a sinusoidal current that is for each phase 120 degrees displaced. And this sets up a magnetic field also in the machine. And then comes the interesting thing, and that is that, okay, I know, hopefully this is working and it's located. Okay, so now I have current going in here, and now it sets up a magnetic field, something. Now it's here, now it's tilting up like this. Okay, and that means that if I go a little bit back here now, now my magnetic field is exactly as on this model. It goes out here, in here. So now it's a north pole when it leaves the steel, and it becomes a south pole here, where it enters the steel in the stator, and the opposite here. But they are just opposing each other, so it's a large force now inside this one, trying to attract this to the stator here and to the stator here, but they are balanced, so there is no net force on the rotor. But the force is quite large inside this machine now. Okay, then I start to turn this one, and then you'll see that now it's very heavy load here. It's a little bit more heavy if you turn it off. Then it's easier, no load, it just go around, and you see here now. Now it stops immediately when I put it on. So you have a braking force then. It's more heavy. And that is due to that when there is a 3-phase current in this winding, they set up a similar field as this one. But it is tilted a little bit. Maybe it comes down here then. And then you will have a south pole here set up by this flux, and a north pole here, and then you have a torque in the machine. And the larger this angle is, the more force you get then. So that is the principle for a synchronous machine, that it sets up a voltage that is synchronous to the speed here. So we have 50 hertz, that is 50 revolutions per second, 3,000 per minute. And then if you like this have 4, then it's 1,500. That is not so important. But this is how it works then, that in a synchronous machine you will have 2 fields rotating at the same speed. The rotor rotates at the same speed as the magnetic field set up by the stator. So when you connect a lot of these machines together, they will all rotate at the same speed. If you load them too much, then this angle becomes larger than 90 degrees, and it tips out. There is no net force anymore. So now, if you are looking, it's very low frequency, this, but you should see that this is on top, then later bit this one, and then the last one. So that is the principle of the synchronous machine, and that is the workhorse when it comes to generate electric power. There are other types of machines. You could replace this one with a permanent magnet that is used in wind power. There's also something called asynchronous machines. I will not go into that, but this is the workhorse for power production. Okay, so then we have the generator. Now we have the power system. How does it work then? At the start, it was very short distance between power generation and the consumer. Let's say Edison, he was starting with DC in New York, and then it was very limited. Then they came up that, oh, I could use AC then. The beauty with AC is this one. You could build transformers, so you could raise the voltage. It's very difficult to have high voltage in a rotating machine. But here in a transformer, you could have several, some 100 kilovolts then. And then you can connect your generator via the transformer to, let's say, this bus bar here at maybe 132 kilovolt. And the energy could go into the central grid, which is mostly at 300 and 420 kilovolt. And it could then transmit this over very long distances. So if you wonder why the old aluminum works and steel works is very located to the power stations and, in our fjords, that was due to the lack of this technology. They didn't have the possibility to raise the voltage sufficiently high to transport the energy. Then you need very large, thick conductors, and that is not economic. So the invention of the transformer, very important for transmitting energy then. And then it comes down to your houses. You cannot have high voltage here. That's quite dangerous. So we are then going down to this voltage system. Let's say the three-phase system, AC, outperformed or were winning then, prevailing over the DC system in around 1890. Edison was losing a huge contract to Westinghouse in New York. Edison was quite nasty. He was saying that AC was much more dangerous than DC because they use AC to kill people in this electric chair. But DC is much more dangerous. So he was wrong, and he lost. Okay, so now we have the power system. So then, how does this work then? I'm here now in the morning, and I'm taking a shower, and I'm heating up some water for coffee, and all my neighbors are doing the same. And then it's very difficult, except for batteries and so on, to store electric energy. So you need to adjust the production then. And that's the next in the power system. So here you see, this is the main central grid in Norway. We have, the majority of production is here. You see, we have power lines over the mountains to the east part of Norway. This is a little bit old, but we have strengthening the connection between along here now. But nevertheless, this is our system. In Sweden, they have a very strong grid like this. Historically, they have all the hydropower along the long rivers in the north and the consumption here then. So that's why the old ASEA became so very good in high voltage, long transmission then. But how do we adjust? All this here is running on the same speed. All machines in this area is one synchronous area. So all machines is at the same speed. So how do we adjust this and balance the load and the consumption? And that is through the frequency. And hopefully this is working. Yes, not bad. Okay, so right now the frequency in our grid is 49.97 hertz, and that's quite good. It should be exactly 50. So what is happening then is that, okay, when I turn on my boiler in the morning, or if I take a shower, it starts to heat up. Okay, when I switch it on, maybe I want to have 1 kilowatt of power to heat the water. Then immediately what happens is that I take 1 kilowatt from all my neighbors. The voltage is dropping a little bit, so I get my power, and they need to give away a little bit. If a lot of people is doing this in the morning, the voltage start to drop, and then some mechanisms in the power system, both at the generators and in the transformer station, do something to adjust it up again, and that is done, and then the generator feels always more heavy. It's more heavy then. Okay, so if I'm just turning like this, here, I feel that, my load is increasing. Then I slow down then. And then all machines slow down at the same pace. Then you have something called droop control in the power station, that if you are dropping, let's say, from 49.97 here to 49.85, let's say one power station here should then raise the production by 50 megawatt by putting on more water. And then that happens at all the power stations, and then you are restoring balance again. And then later on, when everybody is at work and the load is smaller, then it may be a bit too high, and then the same process goes down again. So the communication is the frequency. If it is too low, that is lower than 50, raise the production a little bit. If it is too high, reduce it. Okay, so it's the frequency. So well, let's say we are talking about smart grid today. This is quite smart, and one signal is controlling all the power stations. Then hopefully, if this works here, you can see right now, this is the situation now. Here you see the cost. This is in euros per megawatt hour. So it's almost the same as øre per kilowatt hour. So it's 46 here. You see now it's the same price in entire Norway, also in Sweden. But Finland is more expensive. So then you see power is going from Sweden to Finland. Denmark here, Jutland, is more expensive, so power is going from south part of Norway through the cables here. And in south part of Sweden, also here, but they are exporting here. But maybe this is too detailed, but you may see here then that they are importing a lot here from Poland. It's 600 megawatt. This is really cold, the coal. So and they are importing here and sending it further to Lithuania. It's a strange. So it's Mikael here. He could explain these power flows, but this is the situation. And you see, here we are exporting to the Netherlands, and the Netherlands is exporting back to Denmark here. So this is the situation right now. If you look at this during the night, it might be the opposite. Then maybe I could do that, see what happens then. Then we could see what here, 4 o'clock this morning. Then so the prices is lower, but still we are exporting. But then we are importing from Netherlands, not exporting. And we are importing from Sweden. So this may change during the day. Then. Yeah. Yes, that was the power system in a very short way.